Here we are discussing about a project, a fast and energy efficient level shifter with a complementary output buffer for energy constrained systems. Okay, so here a compact and energy efficient level shifter is essential in voltage scaled systems such as a low power processor, sensor nodes, and memory centric architectures where wide voltage interference and fast signal translations are required. Okay, so here the existing level shifter provides a good conversion range and moderate delay, but they often suffer from a larger transistor count, increased area, higher leakage, and reduced efficiency when operated in deeply scaled technologies. This limitations becomes more significant in memory dominated systems where the level shifter directly affects the stability and rate performance of SRAM cells. So this paper level shifter based and buffer assisted stretches using 7 to 13 transistors and introduced additional parasitic loading and that limit speed and increases dynamic power. Okay, to address these issues, this work produces a optimized and ultra compact level shifter using only 5 transistor count in 45 nanometer CMOS technology. So this design restructured the current mirror and feedback path to reduce the short circuit current and minimize leakage and preserves a voltage gain of about 6.02 dB while cutting a device count by more than half compared to the earlier design. A key novelty of this work is integrated of the proposed level shifter into the 60 SRAM read assist path where the amplified output enhances the bit line and the differential swings improved read stability and reduced latency without adding substantial area and energy overhead. The proposed circuit is evaluated through the schematic level simulation using a Tanner EDA and measuring delay, power, minimum operating voltage, gain and stability under as typical and corner conditions. This results confirms that then 5 transistor architectures assure low power consumptions and reduced delay and smaller silicon area while improving a memory and read performance, demonstrating it a suitability for compact and energy constrained system on chip applications. Now we can verify the paper. So this paper is fully designed for the energy efficient level shifter architectures. Okay, so here already they're done with the 3 number of level shifters in this paper. Okay, so one is for WCMLS and modified WCMLS and optimized WCMLS. The optimized technique is a proposed part of this paper. Okay, so here in this paper the WCLMS means here this one. Okay, so Wilson CMLS. Okay, CM means it's a current mirror and LS means it's a level shifter architecture. Okay, so they prove the differential cascade voltage switch. Okay, so which using this level shifter operations. Okay, at VDDL 0.3 and VDDH 1.2 voltage at 55 nanometer CMOS process. Okay, but this proposed work we proved in 45 nanometer CMOS technology and we plan to reduce the number of transistors count and input voltage and we prove the voltage gain also in the paper. Okay, so the proposed work we have taken from the figure 2 architectures, the proposed LS stretches. Okay, so this one considered as a optimized WCMLS and this one is a WCMLS architectures and this one is modified WCMLS architecture. Okay, so here the figure 2B architectures is the original level shifter method. Okay, so here it will considers only 7 logical count of transistors. Okay, so using this level shifters the modified and optimized architectures both it will be designed in this paper. Okay, so here you can verify it. This one. Okay, so it's a WCMLS architecture and from the modified architectures which using the same technique. Okay, so here this one. Okay, so they plan to using this WCLMS and to improve the performance. Okay, but In the novelty architectures, we plan to reduce the transistors count in the figure B. Okay, so it's using 7 transistors counts. We plan to remodify this architectures with a 5 transistor count, and we prove the same performance of the voltage gain. Okay, so that architectures, it's not to be used again with the optimized and modified base testers. Okay, so where directly used this architectures into the SRAM based architecture. Okay, so here the SRAMs is mostly required to boost the output gain. Okay, so that's why we created a SRAM integrated level shifter architectures as a proposed. Okay, so this work we have integrated a 45 nanometer technology in Tannery DA2. Okay, so now we will verify the step-by-step architecture. So this is the initial design, WCMLS architecture. Okay, so this is a simple designs what they are given in the papers. This is a core. Okay, so it's using 7 transistor count. Okay, so here once we executed, okay, so here the paper they used 1.2 voltage, but we used only 1 voltage, and the input of this pulses, it will be generated from 0.6 only at 20 nanoseconds delay time period. Okay, and this is a VDDL. Okay, so it's also given with a 0.6 voltage. Okay, so here once we executed, we'll get this output. Okay, so this is the input and this is the output. Okay, so it will come with a more gain of level shifting. Okay, so you can verify this output. So this is a existing model, but we designed this work in a 45 nanometer. Okay, and the next one is a modified architecture. Okay, so this one is a modified architecture. Okay, so we can run this. Okay, so verify the input and output part. Okay, so you'll get a proper gain here, so around 0.5. okay, and the next thing is optimized architecture. So this is a proposed architecture of this paper. Okay, okay, so this one. Okay, so here also you can verify the gain value, and the next thing is the modified architecture, what we proposed it. Okay, so that is a proposed level shifter architectures. Okay, okay, so here you can analyze the input and output voltage. Okay, and this part it will occupy only number of count, means MOSFET equal to 5 count only we used. Okay, so here you can analyze the power and area. Okay, so MOSFET equal to 5, and power results, okay, and delay results for this proposed architecture. And using this proposed, we integrated SRAM operation. So BL, BLB, WL and output. Okay, so BL means bit line complement, and WL is a write line. It's just a 60 transistors. Okay, so it will come up with the better in output voltage gain. Okay, so here you can verify it. Okay, so here this is the output. Okay, so this is a write line, BL and BLB. Okay, so this all come with a 0.6 input voltage, but we'll get around 1 voltage is the output. Okay, after the level shifter. Okay, so this novelty architectures integrated with completely 45 nanometer, and we compared this novelty architectures WCMLS and modified and optimized and proposed, okay, with the SRAM architectures. Okay, and we have written an abstract document as a final. So title, base paper abstract, improvement of the project, okay, and proposed title, and abstract, general notes, existing, and disadvantages, proposed systems, proposed architectures, descriptions, advantages, and literature review. Okay, so related notes, everything we have to do, and finally references. Okay, thank you.
Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research.
Introducing NXFE Innovation, your trusted partner in IP design and VLSI research. With over 300 plus completed projects in cutting-edge domains like low-power VLSI design, high-speed data transmission, signal processing, and secure networking, we offer tailored solutions for students and professionals in BE, BTech, ME, MTech, and PhD programs. At NXFE, you not only get expert-guided projects starting from RIS 6000 transparency, but also enjoy unmatched benefits like RIS 1000 to off on your second project, free documentation, and easy-to-understand video explanations. Plus, our rewarding referral program lets you earn up to RIS 2000 MANTs for every successful referral. Trust us to simplify your research journey with high-quality, affordable, and fully customized VLSI solutions. Visit our website to explore a comprehensive collection of projects, organized year by year from 2014 to 2024. The latest 2024 research projects are now available for publication, along with several 2024 non-completed titles, which are updated monthly with new possibilities. For application-based projects, interface designs, and mini projects, you can also rely on NXFE for top-quality solutions. We provide exceptional PhD assistance with full publication support and offer an installment payment option, allowing you to pay module by module. Let NXFE guide you through your research journey with flexibility and expert support. Thank you.